Hello, my name is Tom Webb. I am a postdoctoral researcher from the University of York studying the coastal climate. Welcome to the Cryosphere Pavilion. And also welcome to those of you watching at hubs in Stockholm and Geneva. We are going to have this event now on permafrost emissions and overshoot scenarios. If you have any questions, feel free to ask in the chat, or if you're at hubs, please direct them to your host, and those will be asked in the question and answer session after the end of these presentations. I'm now going to hand you over to Gustav Hugelius from Stockholm University.
Thank you very much for that introduction and correct pronunciation of my name. So I'm going to start by giving really an overview talk on carbon cycle feedbacks, permafrost, and overshoot warming. And if you've been with us all day, you will recognize a lot of this material from an earlier session. But I'm also giving some more perspectives on overshoot warming and the whole concept of what that is and what it means for permafrost. I'm going to show you a lot of material that's from the latest report released by the IPCC. So Working Group 1 report from the 6th assessment report. And in general, just find all of the references to the, either to the papers or to relevant figures in the report in the bottom left if you want to learn more about the material I'm showing, because this is just really an overview. This is from the summary for policymakers. And it's a figure that shows cumulative human emissions on the x-axis plotted against global warming on the y-axis. And basically what you see here is that there's a really almost perfect linear relationship between how much CO2 we've emitted and how much global warming we've seen. So this tells us that really every ton of CO2 released adds to global warming. Another important message from this graph is actually that it could be even worse. And that is because the Earth system is actually absorbing roughly half of the emissions that humans are putting out, either in the terrestrial biosphere or in the ocean biosphere. This line illustrates how the warming roughly would actually look if we didn't have the biosphere taking up so much of the CO2. It would be a lot worse, and it would be really an accelerating warming trend rather than a linear one. Unfortunately, we see that these natural Earth system sinks, they are weakening, and they will be progressively weakening even more with higher emission scenarios. This is another figure from the IPCC report that shows the bars show the cumulative human emissions in different scenarios, ranging from a low emission scenario in blue to the left to a very high emission scenario in red to the right. And then you see, the total portion that ends in the atmosphere is this gray upper bar, and then you see you see the chunks of those emissions that are actually going to be reabsorbed into the Earth system, and thus cooling the climate, or not cooling, but limiting the warming, the ocean or the land. And what we see is that in the low emission scenario, the Earth is going to be doing us the favor, actually absorbing 70% of our emissions. But if you go to the high emission scenarios, these sinks really saturate, and only 38% of the human emissions can actually be absorbed back into the system. I'm going to get back a little. So I'm going to get back to part of the mechanisms of why that is in a while. Also here, I want to highlight a few of the take-home messages that the IPCC listed on carbon cycle feedbacks in the summary for policymakers. They find that carbon climate feedbacks, so Earth system feedbacks that actually warm the climate even more in a feedback loop that makes global warming worse, they increase with warming, and they become more uncertain with warming. So our ability to project these feedbacks actually becomes smaller and smaller, the higher the warming is, basically because of unexpected or behavior in the Earth system, and also because we are moving the Earth so far out of the envelope of where it's been before, that it becomes more increasingly difficult to actually model these processes. But with that said, the IPCC also find that the different scenarios, the human emission scenarios, the SSPs, still dominate uncertainty in the magnitude of future atmospheric CO2 concentration. So most of the uncertainty still comes from the human behavior, as opposed to our imperfect understanding of the carbon cycle feedbacks. Another important point is that some really large carbon cycle feedbacks are not included to the CMIP6 or the AR6 models. And this will cause even higher CO2 and methane emissions than what we see in most of the graphs and so on. And the key ones are wetlands, permafrost thaw, and wildfires. And I'm going to zoom in more on the permafrost thaw aspect of it soon. We've heard about wetlands and fires in earlier sessions today as well. This graph shows you the carbon cycle climate feedbacks that are in the models. I just talked about the ones that aren't, but many of the processes are, of course, included in it. I mean, the models are dynamic; they have vegetation changing with emissions, etc. And this is another figure from the IPCC report that breaks this, the most important feedbacks into a couple of different categories. The two top ones that are blue graphs, they are the land and the ocean carbon response to elevated CO2 in the atmosphere, which is actually a really strong cooling feedback. So the more CO2 we put in the atmosphere, the more productive plants are, and the more rapid the exchange between the atmosphere and the sea surfaces. So basically, carbon dioxide has been taken up by ocean, causing ocean acidification. But these feedbacks are still cooling the climate quite a lot. On the lower two lines, you have land carbon and ocean carbon response to climate. So the first, the cooling feedback is response to more CO2 in the atmosphere. The warming feedbacks we see here, they are responses to the actual warming of the climate. That anything as soon as temperature increases, chemical reactions are speeding up, and you actually see a more rapid degradation of carbon stored in soils, or an acceleration of the ocean carbon climate cycle, which leads to these positive feedbacks. And if we go to a graph of the global carbon cycle, here there are a lot of arrows showing the sort of natural state of the carbon cycle, more or less. And there you see the numbers of fluxes or of pools in yellow and blue text. I'm not going to go through all of them, but we see that these are all very big numbers. The unit here is gigatons of carbon. So if you want to convert it to gigatons of CO2, you have to multiply it by 3.7. So if you don't recognize the numbers, that's because of the mismatch in units. But what I want to focus in on here is the red numbers. You see the human emissions in the middle there, 9 petagrams of carbon per year, roughly equivalent to 33, 34, 35 petagrams of CO2, depending on which of recent years we're talking about. But then you also see in the uppermost left corner, you see 120 plus 3, if you can read that. And the plus 3 there is actually the cooling carbon cycle feedback of increased photosynthesis due to CO2 fertilization. And you have a 90 plus 2 when it comes to air-sea gas exchange, which is, again, this cooling feedback that even more CO2 is being taken up by the ocean due to human emissions. So those red numbers also show human perturbation to the climate system. And this next graph, again from the IPCC, shows us carbon cycle climate feedbacks that are missing in the Earth system models. I already talked a little bit about this. And here we see that the IPCC report actually quantified these, even if they're not in the models. They used, meta-analysis of existing literature and actually calculated roughly the size of these feedbacks. And so you have fire response to climate, permafrost response to climate when it comes to both CO2 and methane, and then the wetland methane response to climate. You see, these are all positive feedbacks. These are all warming the climate further. And if we add them all together, they equal roughly 5 to 10% of total human change in radiative forcing. So it's quite a significant additional feedback on top of other, on top of the more direct forcing from emissions. And by far the biggest one is permafrost response to climate. The methane response might actually be a little bit underestimated here still, but it's really progress that the IPCC have quantified these feedbacks, and they're also accounting for them in projections of remaining carbon budgets to stay at under certain climate targets. Okay, but zooming in a little bit on permafrost. The session is about permafrost thaw and overshoot. The permafrost thaw is a warming feedback. You have a very large area of permafrost in the northern hemisphere. Roughly 20% of all of the land surface in the in the northern hemisphere is affected by permafrost. So you have several million square kilometers. And as global warming thaws permafrost, there are enormous amounts of carbon that's been locked into permafrost usually for thousands of years, that can be accessible to microbes as temperatures warm, and the microbes start to degrade this, and they produce methane and CO2 as byproducts. The permafrost region stores more carbon than the whole atmosphere and all plants living on Earth combined. So it's really a problem, or it's processes of a massive scale, and it's also processes that act over a very long time scale. So it's a system that's relatively slow to respond to climate warming, but once it starts to respond, the response is almost inevitable on policy relevant timescales. And this becomes especially important when you get into the topic of overshoot warming. So what is overshoot warming? I've tried to illustrate that here in this simple conceptual graph where you have time on the x-axis and temperature increase on the y-axis. And the black dotted line represents the target temperature. Let's call it 1.5 degrees if we're optimistic. And then you have basically two ways of getting there. You have the really nice way in the green line, which is rapid emission reductions to just reach the target temperature and stabilize. And then you have the other option where you actually overshoot the target temperature, keep emitting fossil fuels for a few more years to buy yourself time to sort of restructure your economy or whatever reason you have for wanting to keep emitting. And then you rely on negative emissions technologies later on to pull those emissions back down into the atmosphere, and you get an overshoot warming that goes above 1.5, perhaps up to 2, and then down again. And the problem is that a lot of the Earth system feedbacks are going to be triggered by this overshoot warming, and some of them may not be reversible. So if we add permafrost to this, the first problem is that the permafrost drives further warming that might be even stronger. So you actually get an even higher overshoot than what you had initially planned. And the second problem is that to a large extent, there's going to be irreversible permafrost loss. Permafrost doesn't grow back very easily, at least not all sorts of permafrost. And the permafrost thaw also triggers carbon loss that persists for centuries. So you're sort of you're triggering a problem that doesn't back down when the climate backs down, essentially committing several future generations to have to deal with these increased emissions for centuries. And the key aspect here is that permafrost is not just organic material or soil. A lot of it is massive ice in the ground. And this has been built up. There are a lot of different types of massive ice, and there's a whole scientific discipline dedicated to the study of permafrost ice and its ice bodies. But the common denominator of most of this massive ice is that it takes a really long time to build up. And when we thaw it, perhaps during this overshoot time, the ice melts, it drains away, you get collapse of the whole ground surface. And also, even if the climate is brought back down, the ice is not going to regrow anytime soon. That will take centuries or millennia. So the permafrost thaw that is triggered in this way will keep emitting carbon in these thermokarst or abrupt thaw landforms for a very long time. And we see this happening already. It's observed. This is from scientific papers observing this in very cold parts of the Canadian Arctic that should still be frozen at least for another 70 years according to models, but it's already happened. And this is a response where you see massive abrupt thaw really changing the whole landscape in response to a few summers of regional heat waves in the Canadian Arctic that happened a few years ago. And in the last few summers, from news reporting that there's been even more extensive heat waves across all of the Arctic, which in turn has certainly triggered even more massive thaw that is making the situation worse. And this is a slide that shows observed permafrost extent with a combination of remotely, so using satellite temperatures and the state-of-the-art model. And that was 2003, 2010, 2017. So if we go back and forth, you see very rapid loss of the near surface permafrost over just a few decades. I want to emphasize that in a lot of these areas where the permafrost disappeared, you might have deeper permafrost still there, but this is really the near surface permafrost that is being thawed rapidly. And this is also happening more quickly than what models had projected for this time period. So the IPCC also asked the questions, which is very relevant to overshoot warming then, is could climate change be reversed by removing carbon dioxide from the atmosphere? And you see, their conceptual overshoot warming scenario there, where you have a very pronounced CO2 peak, and it goes back down, and it stabilizes around 400 ppm in this example. And their answer to this question, it varies depending on what part of the climate system you're talking about. You can reverse it if you're talking about global surface temperature. There's a lag time of a few years, but then models project that temperatures would stabilize if we could use negative emissions and draw them down. Other Earth system components have lag times of decades to centuries. Here they project that the permafrost area will stabilize after a few decades, but note that it's stabilizing at a much lower level. And yet other Earth system components, they don't stabilize at all. Well, they might in a very, very long time. But here you see, millennia, centuries of ocean thermal expansion just keeps going. Over there, and you have ocean acidification is another example of processes that move over extremely long time scales. So you can't just flip them around and back them up again. Ice sheets are the same. Once you trigger those dynamics, it's really hard to back down from it. I'm going to go back to the permafrost example again. And here the IPCC says yes, but decades of lag time. But in reality, these huge areas of permafrost that we already lost, they are going to keep emitting permafrost carbon for centuries. So there's a lag time of decades in the area, but there's a century scale lag time in the actual emissions, because you have already lost several million square kilometers here, and they are irreversibly lost in this scenario. So what does this mean then for sort of estimates of remaining carbon budgets? For the first time, well, not for the first time, but in a more detailed way, the IPCC have actually included permafrost carbon in these numbers, which is really nice. Now I just moved it from the gigatons of CO2 remaining to us to years remaining to us if we think about emissions equal to last year. So you have 1.5 degrees warming, 1.7 degrees warming, 2 degrees warming, and different sort of levels of chance to reach that target. And if we want to be on the safe side and say have an 83% chance of landing at a certain target temperature, we have 9 years still of emissions to reach the 1.5 degree target, almost 30 years to reach the 2 degree target. Unfortunately, there are processes that we are becoming to understand that might point to this even being optimistic. You will hear more about this in later talks. Unfortunately, we're in a situation where we see that carbon dioxide emissions from human sources have rebounded from the COVID-19 pandemic. This is a figure from a non-reviewed preprint of a scientific paper. You see the reference at the bottom. And it just shows the projected emissions going to the end of this year. So this projection puts 2021 just 1% lower than 2029. So than the highest pre-pandemic emission year that we've had on record. So we still might be 1% lower, which means that we actually still have a chance to say that 2019 was actually peak carbon, was the year where we had the highest emissions, and we still have a chance to actually go. If we go down again, 2022, perhaps peak carbon has passed. Perhaps it hasn't. We'll see what this conference and other efforts where they get us. Okay, so to summarize, we see that the natural carbon sinks in the Earth system are weakening. This differs with different scenarios. The CMIP6 Earth system model, so that's the ensemble of models used for the last IPCC report, they lack some really important long-term feedbacks, including permafrost. But they do, in the report, quantify these missing feedbacks and accounted for them in the remaining carbon budgets. That give us about 8 to 9 years to stay below 1.5 degrees if we stay at the path we're on. And the IPCC also conclude that CO2 removal can rapidly limit global surface warming, but other Earth system components will lag anything from decades to millennia, and that includes permafrost, most certainly. And another important message to also bring to the next coming talks in this session is that overshoot warming, if it happens, will trigger irreversible permafrost thaw that will drive additional warming for centuries, even after the climate stabilizes. Thank you. Okay, so that was our sort of initial talk, and now I'm going to hand the word over to Jens Strauss from the Alfred Wegener Institute, who's going to summarize a recent chapter he published in a volume by the UN FAO organization. So please.
So thank you. Actually, it's a chapter we published, Gustav. So thanks for this kind introduction. Yeah, the chapter I was, I will talk about. Like, I named this talk "Hotspot Permafrost: Importance of the permafrost as a major carbon stock." At first, right? But as introduced before, this talk is very close to this report. It's called Permafrost, and it's part of this recarbonizing global soils. And there it's a second volume, hotspots and bright spots of soil organic carbon. So the aim of this talk actually is to give you a better understanding of permafrost as a global relevant carbon storage and the challenges and trends which comes with permafrost carbon mobilization. So to just remind you what is permafrost and why it's a hotspot. So permafrost is ground which is frozen for more than 2 years in a row. But actually the permafrost I am dealing with, we are working on, is much, much older. Lots of it is coming from the last ice age. And actually the permafrost region is the biggest part is located in the northern areas. So it's 21% or 25% of the northern hemisphere. And here you see the map of the permafrost region. There, on the other side, you see where was the highest temperature anomaly last year. So you see this red dot there, and it's exactly on top of this permafrost region. So this region, gets a lot of energy, a lot of temperature put into it, and this, of course, causes problems, right? Yeah, so this actually answers already the question which I'm raising up here, but I just want to show this image, why we are interested in permafrost. Permafrost looks like this. Normally it looks like tundra or boreal forest, but if you have the chance to look from the side, you see here the permafrost, and you see the active layer and the vegetation. The active layer actually is a layer where the summer heat is thawing and the winter cold is refreezing it again. So it's a seasonal unfrozen layer. You see the same thing in my sketch there. There's ice in there, there's permafrost, there are unfrozen zones, we call them talik, and there's the active layer on top. Actually, permafrost is thawing, and Gustav said in some regions 70 years faster than expected before. So this puts permafrost at risk, and it causes consequences. The consequences are on every scale. There are local and regional consequences like ecosystem changes, disturbance by geochemical cycles changing, and there are global consequences. The global consequences actually are like the permafrost carbon feedback and the influence on the climate greenhouse gas emissions. Here, just a short reminder that permafrost is at risk. So we see here the 1950s to 2100s development or expected development of the permafrost area in the top 3 meters. And you see 2 scenarios, the 8.5 and the 2.5 scenario. The 8.5 is a current trajectory, and the 2.5 is the mitigation scenario. So when we do something to get the greenhouse gas emissions not that high. Actually, what I want to show here is that even in this 2.5 mitigation scenario, we expect a permafrost area loss of more than 25%. If we follow our trajectory, which is happening right now, we can lose up to 75% of the permafrost area until the end of this century. And if you lose this area, you lose a lot of stuff which is in there, like ice and carbon. So here you see a map of Brown et al. Showing that permafrost contains ice, sometimes a lot of ice, sometimes medium ice, sometimes not that much ice. But actually, my research is focusing also on Yedoma deposits, and Yedoma is a very special kind of permafrost. It is a very ice-rich permafrost. Up to 80% of this deposit can consist of ice, and moreover, there's a lot of carbon in there, like this peat layers you see in this soil column there. Actually, the Yedoma deposits, the Yedoma area is about 500,000 square kilometers. This is quite a lot of Yedoma out there. And yeah, in general, we have up to 1,600 gigatons of carbon in the permafrost zone. You see this here. And this is a bit less, but nearly twice the amount of carbon which is in the atmosphere. Of course, the atmosphere is gaining every day and every hour, so this comparison lacks right now. But anyway, so there's a lot of carbon in there. And even though it's just 15% of the global soil area, it stores more than 40% of its soil carbon. And in this permafrost area, there's around about 1,000 gigatons frozen in, which is right now not part of the active carbon cycle. It is sequestered, frozen. But as permafrost becomes impermanent with warming, with higher temperatures, and with our scenarios we are talking about, there are processes being able to reactivate this carbon by thaw. And reactivation means greenhouse gas emission in the worst case, right? But actually, why there's so much carbon in the permafrost? So there's not that many plants out there, not that many vegetation on top, compared to the temperate or tropical ecosystems. But like there was a long time, and there was low input, long time, and even lower degradation. So this leads to the buildup of a huge stock. So a dynamic stock in general is affected by carbon inputs, carbon stabilization, and destabilization and exports. So input is, like always, plant material. Stabilization in the permafrost is mostly freezing, right? And the destabilization is also very, very unique in this area. I put a sketch right there out of a paper accepted last week in Ambio. So you see here that there is carbon input, this arrows down, there's carbon output, this arrows pointing to the atmosphere. But there's also, if the carbon is like mobilized, it's transported. So there are a lot of ways getting this formerly frozen carbon exported or mobilized. Okay. How is this carbon being mobilized? So this is a photo show of different deep disturbance processes. You see on the upper area there, this is thermal erosion, when there is degradation, and then there's a channel, we call it thermal erosion. There's ice wedge. So ice wedges are these wedge-shaped bodies of ice you saw in the pictures before. If these degrades, then there is like an area which is then looking like this. And this is an area in Churabcha. There was an air strip, and this airstrip is right now degrading. Then there's river erosion, there's coastal erosion. And on this picture there, this is the Lena Delta eroding the cliff of Soposise, which is a Yedoma cliff. And also with thaw slumping here, you see this up to 80 meters high wall in the Batagai mega slump in Siberia, which was likely caused by a fire event or a track of like a road, and then there was like this huge slump being developed. And actually, one of the major processes getting deep carbon activated is thermokarst lakes and thermokarst processes. Here you see an initiating thermokarst lake by ice wedge degradation. And on this other, in the center picture, you see that permafrost is, the thermokarst is a local process with the process, but it's actually happening everywhere where there's lots of ice in the permafrost. And this thermokarst, as said before, is the key for getting carbon out of the permafrost. So we have this thaw bulb underneath every lake, and this causes year-round unfrozenness of the soil, and there microbes can produce greenhouse gases. When there is no oxygen, also methane, right? And so there's a lot of processes going on. It's all in this caption, but you don't have to read it. There will be a paper out soon explaining everything. The punchline here is thermokarst thaws deep, and thermokarst causes greenhouse gas emissions. Even when it's draining, when there's no lake anymore, there are still higher greenhouse gas emissions from these areas compared to these areas here which are undisturbed. So in the FIO report, I wrote something about the potential mechanisms how to get additional carbon into the ground. But for the permafrost region, this is a very unlikely scenario because plant biomass is much, much smaller than soil organic carbon, and future vegetation has, because of its size and it's the time, we have a limited capacity to compensate for these emissions we see right now with the thaw. And Gustav talked about peats and wetlands before, and peat, even re-wetting former wetlands, is a process which is very slow. And this paper by Gustav published last year, it shows that even under current projections, we still have an carbon loss from peatlands, a net loss. So these two mechanisms are not able to compensate for the carbon losses we see in this region. And then there's another thing. So we see warming of the permafrost everywhere, and this is from a paper from a colleague, Boris Biscarbon. So they show that 0.4 nearly degrees of warming was per decade was happening from 2008 to 2016. And then the next talk, there will be a lot of projections and future trajectories and emissions. But this paper I cite here, they show that there are loss potential. There's a likely loss between 80 and 650 gigatons of carbon until 2300. So there's a huge loss potential because of warming, and this is also what our models are showing. So direct human agriculture activity has also some impacts on the permafrost, for sure. So there is the use of thermokarst basins as pastures and haymaking areas in Yakutia. Of course, this is removing plant material, and there is carbon out of the system in this particular case there. Increased emissions are also there when there are humid grasslands in hot summers. So there is, when there's use of the land, there are these grasslands which are temporarily flooded, and then there is CO2 and the methane coming out of it. And if there's an intense use on ice-rich permafrost, we see thaw processes which degrade it so deeply that there is an artificial thermokarst lake in this former thermokarst, in this now drained thermokarst basin. And this has a significant influence on the CH4, so methane emissions. You can see this on these pictures here. So this is a haymaking Yukachi, Alas in central Yakutia. And this is one of these two intensively used pastures, and then there's water standing there. So what are our ways for minimizing the threats to the soil functions of the permafrost regions. Actually, because it's a huge area, I said before, 25% of the Northern Hemisphere land area, it is not possible to do on-ground interventions. You can't cool such a huge area. So it's not feasible at all. And one of the slogans of this pavilion was, there's no way, so there are no, the melting point of ice does not adhere on our negotiations, right? So the only way to minimize the threats for the permafrost region is to reduce our anthropogenic climate pressure. That's the point. Because challenges we face when permafrost is thawing is that they are irreversible on human timescales and also on our ecosystem understanding. Even if we stop right now with our emissions, Gustav said that before, the permafrost region will continue because it's an process we started and the ball is rolling right now, and they keep emitting even if we stop emissions right now. So there are lots of risks and there are lots of challenges to adaptation. And I think overshooting, this session topic, is a high risk. And we know if we overshoot, this system won't stop if we want to go down with negative emissions at the end. And you see here again this animation of the permafrost carbon feedback. So everything we warm in air temperature will cause more permafrost thaw, which will cause microbial activity, which will cause greenhouse gas emissions. And this again will cause more warming. And so on and so forth. Okay, this is another trend. So we expect, as shown earlier, also in the midterm and long term, more thaw. Here I put a very new animation by a colleague from Avi. You see on this side there, this is the thaw depths 1800, and here you see the thaw depths in 2100. All these dark blue things is the thaw depths of like around 0 to 1 or 2 meters. And all these colors are thaw depths which are deeper than that. And you see the thaw depths, like the area here. And on the other side here, so it's going up north. So we see a permafrost pressure, permafrost loss everywhere. And there are unavoidable consequences with that. So there is melting of ground ice. There's the loss of Unoma areas. That there will be rock falls, or there are rock falls because of unstable permafrost in the mountain areas. But actually, it's not an all or nothing question. If we reduce our emissions, if we reduce our anthropogenic pressure on the climate, this helps to keep as much carbon as possible in the permafrost zone. This is the animation I was talking about. So if you just want to play with everything, this is very cool. It's not published so far, but will be soon. You have temperature, thaw depths, and soil carbon to play with here. And so actually it's very cool. But maybe wait for another few weeks and then you are able to access this. And this leads me to my take-home messages. Thaw and release of just a fraction of the permafrost will cause more warming and will magnify the global warming pressure. And this, of course, will further degrade more permafrost areas, which will then cause more greenhouse gas emissions. And there are processes also remobilizing the deep carbon. So it's not just the carbon in the first 3 meters, it could be up to 20 or 30 meters. And but actually there's no explosion of this permafrost carbon feedback. It's a continuous process. So there was a change, or there is a change from the Arctic from being a sink to a source, but it's not an explosion. It's continuous, and it will be more in the future, but without any bomb. And actually it's very unlikely that we can compensate on sites for the losses. But actually, as I said before, it's the overshooting is a very risky thing because this is a slow system keeping on emissions even if we have negative emissions. That's it for now. Thank you very much for listening. And again, if you want to read more, the FAO report is out and it's really accessible. You can see it there. Thank you. The next speaker will be Sarah Chadburn from the University of Exeter, telling you about the modeling part of the overshoot scenarios. Stage is yours. Thanks.
Oh, thank you. Just wait for my slide. Oh, here they are. Great. So, yeah, it's great to be here. Can you hear me? Is that better? Fantastic. Yeah, so as Jens said, I'm going to be talking a bit more from the modeling point of view. Again, it's sort of similar messages to what we've heard already in this session, and some more about carbon budgets. So first of all, climate models. So we will all acknowledge the important role that climate models have, warning us about the consequences of climate change. And models, in some form, give us our carbon budget. So they tell us how much carbon we have left to emit before we cross a certain temperature threshold. And as we know, this isn't very much. And these models are they're the work of thousands of people over tens of years, which are bringing together all of the knowledge and expertise and eventually resulting in these models, where we've essentially built a computer simulation of the whole Earth, which is an amazing human achievement. But as you can imagine, it's also incredibly difficult. And these models, in the end, they're only as good as the understanding of the Earth that we have and that we put into them. And this is all very much true of permafrost. We're talking about the future of permafrost, and so we need a model like this in order to predict it, in order to know what's going to happen. But permafrost is very difficult to model and it's difficult to measure. One of the reasons is the complexity of the landscape that you can see, for example, on that picture. Another reason is the difficulty of actually accessing a lot of these areas and measuring what's there. So it's only quite recently, and actually only in the most recent IPCC report that permafrost has actually been included in the carbon budgets. So they have included the carbon emissions from permafrost into the carbon budget. And this is what the report says. So the IPCC tells us that between 14 and 177 gigatons of carbon dioxide will be emitted from permafrost for every degree that we warm the Earth. And as I said, this has been accounted for in the carbon budget for the first time for this report. And this graph is basically showing the same thing, but it's showing what this means for different levels of global warming, for example, 1.5 degrees, 2 degrees. And you can see, so that range of numbers on the left is really a wide range of estimates. That's what those lines mean. So there's a lot of uncertainty. But the one thing that the models really agree on is that the more warming you have, the more carbon is emitted. So that means the warmer the Earth gets, the more carbon we have coming from permafrost, and that makes it even harder to prevent the warming, even harder to stop the warming. So the sooner we stop the warming and the lower level we keep it, the better this is. This is kind of a double win if you're thinking about permafrost here. So, as I said, this has been included to some extent, but permafrost is not still fully understood, and the future of permafrost, we're only just starting to quantify it. So, one of the big things that we're only just starting to make estimates of is the carbon emissions due to abrupt thaw. And this has been difficult because abrupt thaw is something that occurs on very localized areas. It occurs quite quickly and dramatically. There's a lot of complex things going on here, and so it's hard to predict when and where this is going to happen, and to predict what will happen to the carbon as well when this takes place. But we do have some initial estimates. So we have this paper by Turetsky et al. Last year, where there was actually an estimate of how much carbon these processes might emit. And the initial results are not good news. So what I've done here to illustrate it is essentially add these numbers on to the numbers that I previously showed you. So in black, we had those emissions from permafrost that we had under these different levels of warming. And then in the purple, that's adding on the estimated emissions from abrupt thaw. And so now we have between 50 and 240 gigatons of carbon dioxide equivalent emitted from permafrost for every degree of global warming. And I'm saying carbon dioxide equivalent here because actually from these processes, a lot of the warming comes from methane emissions, so not just carbon dioxide. And if you look at the graph, you can see this is increasing the emissions from permafrost by roughly 50%, although, as I said, that there's obviously these large uncertainties and ranges. And so what does this mean for the carbon budget? So one way that we can think of permafrost is, so it's emitting carbon, and you could compare the amount of carbon it's emitting to a major emitting country or a major economy at the moment. But the difference between, hopefully, the difference between permafrost and the countries that are currently burning fossil fuels is that permafrost is not going to be reaching net zero anytime soon. As the others mentioned, it can continue emitting carbon over a long period of time, and the country of permafrost has not signed the Paris Agreement. So all that I've done here is these additional emissions from abrupt thaw that I showed on the previous slide. I've just taken those off the carbon budgets that we have just to show kind of how big those might be. And it's around 10 to 20% of the budget. But all of these budgets assume that we're approaching these temperatures, so 1.5 degrees or 2 degrees, we're approaching these temperatures from below. And we're just stabilizing and gradually reaching them. But the topic of this session is overshoot. And if we, in fact, increase the temperature beyond these targets and then rely on negative emissions, which we perhaps wouldn't think was a good idea in the first place, if we are relying on these negative emissions to bring the temperature then back down to these target levels, then it is a very different story in terms of permafrost. To just show you what I mean by an overshoot scenario. Oh, this is the wrong slides. Could you switch to the other slides? I sent Gustav 2 this morning. I'll talk about this slide while you find the others. So actually on the left, you can see an overshoot scenario. So the yellow line on the left is a temperature scenario that overshoots 1.5 degrees, and then it's coming back down to 1.5 degrees. And the blue line is just reaching 1.5 degrees from below. And the yellow example is not overshooting a huge amount. It's only like by a fraction of a degree and not for very long. But as you could imagine, the higher the temperature gets in the overshoot and the longer it lasts, the worse this is for permafrost. Are you ready? Shall I just carry on? I'll carry on. So essentially, as the others have mentioned, permafrost emissions are irreversible. So the carbon that's in permafrost has taken thousands of years to accumulate. And so anything that we emit during an overshoot, even if it stops being emitted because we brought the temperature back down, even if emissions were to stop, then everything that has been emitted so far, it would take thousands of years to rebuild that carbon in the ground. So we might have the right slides. Oh, that's strange. Okay, well, I was going to show you a picture of some thawing permafrost next. Yes, this is it. Fantastic. Okay, here's the picture of the thawing permafrost emitting its carbon and methane into the atmosphere, and that there it will stay. So now let's look at some numbers. So obviously, the amount of carbon that gets emitted from permafrost during an overshoot will depend on how long that overshoot lasts for. But these are the modeling studies that we have, which is not a huge amount. So I've combined these to get what estimates that we can of how much emissions we would get during an overshoot. In the purple, those are the permafrost emissions that I showed just a minute ago. That includes the IPCC estimate plus the abrupt thaw emissions. And then in yellow and red, we progressively show how much emission we might actually get if we overshot first by 0.5 degree and then by 1 degree. And as you might expect, the emissions are higher the more you warm. So that 1 degree overshoot is roughly doubling the emissions that we get from permafrost. So obviously, if we have these extra emissions, this means that our carbon budget is going to be even smaller. And in terms of numbers, 0.5 degree of overshoot could reduce the carbon budget by more than 100 gigatons of carbon dioxide equivalent. And actually, if we overshoot by a whole degree, then this could actually be the majority of the carbon budget for 1.5 degrees. So yeah, this is the plot again of the carbon budgets with these numbers taken off them. And you can see that actually, so what I've shaded out is the high end of the estimate, and then the blue bar shows the range of the estimates. But at the high end of the estimate, that's using up half of the carbon budget for 1.5 degrees. And what it means is that if we actually overshoot, it's going to take a lot more, not only negative emissions to bring the temperature back down, but a lot more negative emissions than we might have expected. And it can make it really, really difficult to achieve. So those blue bars, that's showing the uncertainty in the estimates. You can see that that's pretty large, and that's highlighting what we have yet to understand scientifically. So just to highlight a couple of the big scientific questions and unknowns, so that contribute to this really wide range of estimates. One of them, you might expect that we would know how much carbon was there, but actually this is quite difficult to quantify and be certain about because it's all under the ground. You know, you can't see it from satellite. You have to actually go there and measure it to be sure. And then a really big question is how quickly would that carbon be released? So the permafrost might thaw, the carbon's now thawed, but how much of that would actually be released from the ground and how quickly is really uncertain. So that really highlights that we can't just be using our models to ask what is happening to permafrost. We also need to be looking at the permafrost and asking what does the permafrost tell us about our models, how can we improve them and constrain this. So to summarize, the IPCC have for the first time included the permafrost emissions in their carbon budgets. or at least some of the permafrost emissions, but there are processes that we haven't yet fully quantified that are not yet included, and these tend to make things worse. So this includes abrupt thaw, which I showed you some figures for that, and that can reduce the carbon budgets by around 10 to 20% extra. And then also multi-century emissions, so permafrost continuing to emit further into the future. So permafrost emissions, as we've said several times in this session, are essentially irreversible. And the more warming we have, the more emissions we get. And this makes overshoot a really big problem. It means that if we overshoot, for all of that time that the Earth is warmer, a whole lot of carbon gets emitted into the atmosphere and then it stays there. And that makes it really difficult, or at least a lot more difficult to bring the temperature back down. And it can, if we overshoot by a whole degree, which is not implausible, I would say, then we could use up most of the carbon budget for 1.5 degrees, and that can make that incredibly difficult to achieve. So this really highlights the urgency of, well, first of all, constraining the sort of scientific knowledge further, but more importantly, the urgency of acting to keep global warming as low as possible and really to avoid overshoot if we possibly can. So you can watch all these talks again on this website if you want, and these are the references that I used. So thanks. And the next speaker is Ug, who is going to talk about coastal erosion, I believe.
My presentation, I don't know if you can hear me well. Yes, my presentation is going to be very quick, actually, and it is very much a continuation of those 3 talks. And I'm going to show you two recent papers that try to map out or understand or quantify or first quantify the impact of one of these processes that we knew of. I would call them known unknowns, and that we think might be actually worsening the situation or actually accentuating or increasing that negative impact. The first one of them is coastal erosion per se, and the release of carbon that is stored in the permafrost. We saw that these huge quantities are there to the nearshore zone. That means the immediate coastal area, so in front of your shoreline. We are not saying that once they are released, those huge quantities of carbon are actually directly transferred to the carbon budget in the atmosphere. What we are saying is that those lateral fluxes of carbon will be added to the nearshore zone, might actually feed into the ecosystem, contribute to alter the trophic level, so have ecological consequences, but also potentially some climate consequences. What we know for sure is that coastal erosion is increasing dramatically right now. I've shown some slides this morning that we have some places where it increased from 0.4 meters a year to 8.8 meters a year. This is very drastic and a huge threat for a lot of the communities that are located along the coast. But here we are really talking solely about the carbon impacts. This is a recent paper that is put forward by David Nielsen with a group based at the Max Planck Institute in Hamburg, which is part of the EU project I'm leading, which is called Nunatak. And here we are looking at the development of coastal erosion and different kind of scenarios for the erosion rate. And I'll also show what that means in terms of release of carbon. On the x-axis, you have the times, that's pretty easy to see. And on the y-axis, you have the meters per year. What we know is that right now in the Arctic, we have an average rate of erosion of 0.57 meters per year, which is quite substantial already. And this is where we are. We know that erosion has been increasing over the past decades. We are now approaching, you see, the 1 meters per year, and so increasing substantially that rate of erosion. Now, building on a model that is purely a statistical model, but that remained the first attempt to model coastal erosion in the Arctic at the circumarctic level, we were able to put those two numbers together. These are based on the SSP 2.5, and then they show you those two trajectories. And the take-home message here is that we are getting completely out of the historical range in terms of coastal erosion, and we will land with average erosion rates for the Arctic between 2 and 3 meters a year until 2100. Now, what that means is that if you think the erosion as a piece of cliff that is leading to the ocean, you're gonna now double the volume or triple the volume that you're gonna release every year. So the impact in terms of release, in terms of quantities of carbon, are huge, because you can rapidly double the quantities that you release to your nearshore zone with unknown consequences. So this is what these bars are showing you, is that really we are now outside of the historical range. What does that mean in terms of carbon? What I'm showing you on that left chart here, which is taken from the same paper, is what we think we know about the release of carbon from coastal erosion. Generally, like estimations, because of the lack of data we have for the area and the lack of control, range between 6-8 teragrams a year to up. Some estimations were up to 44. They are not listed here. Generally, we think that we are basically around between 3 here and 14 teragrams of carbon per year. This is already very substantial. This is in the range of what is being provided by rivers in terms of particulate organic carbon. But the thing is that the coastal erosion has much higher potential to double or triple than the discharge of river does over the same areas until 2100. So this could have very substantial impact. Now I'm going to show you the range of carbon that we're going to get following those two scenarios on the right here. And this is it. Now we are reaching with maximum values of 20 to 25 teragrams compared to the average values we had before. We are really doubling those quantities or tripling in some cases. What that means is really unknown to us at this stage, simply because we don't really understand either the ecological consequences of these increasing quantities of carbon being released to the nearshore zone, but also the climate consequences, because we don't really understand what's happening to that carbon. We're moving into that direction by mapping out on the shelf, and I think Paul Overdin showed a beautiful diagram this morning of the database of sediment on the shelf. So we're starting to understand how much is being deposited. We see some carbon, though, going somewhere we don't know, and we don't understand why it is. And what we want you to do is to tackle that issue and devise an experiment to see whether part of the carbon that is taken from that cliff that was previously frozen and is now landing into the ocean has the potential to be actually released into the atmosphere once it touches basically the water. So what we did is a fairly simple experiment. We took a lot of samples of permafrost that we had, and we took some samples of seawater with the microbial organism from the exact location where we took the samples, and we incubated those samples with different kind of controls, temperature scenarios, etc., and we started to look at it. And basically, I'm going to show you the result here. So what you're going to see on your y-axis is the cumulative production of CO2 over time. And then on your x-axis, this is the time. Notice that we use 120 days. This is about 4 months. This is kind of the length, approximate length. It depends from place to place, obviously, in the Arctic Ocean of the open water season. The open water season is where those processes are likely to happen, where you have erosion, storms eroding that carbon, falling into the sea, and potentially releasing some carbon dioxide. Notice that I don't have the results here, but we also measured methane, but I'm not going to show that today. Here is CO2. So what we did first is to have a control. So we took those samples and we also incubated them in the air. The reason behind that is that there's already a lot of publications on incubating permafrost in the air. That reflects the processes that were very much addressed by our three previous speakers. So by doing so, we could see that we were in the range of the experiments that were published earlier. And this is what got out of the permafrost if we incubated it in the air. Now, The state of the art was that if we put it in seawater, not much would be happening because we think that much of the carbon that is bound on that sediment is going to land on the seafloor and it's going to get buried there. Or generally what happens is that it doesn't stay that very dynamic zone. It gets resuspended and gets exported longshore, but most likely offshore to go somewhere where it's much quieter, than settles on the sediment. In some favorable condition, it might not get degraded too much by the microorganism and stay there. This was the theory. So we thought we would actually see something. And as any scientist does, you were hoping you would get to see something maybe a bit more substantial, and so that it would be a story to tell. But this is actually what we saw. So actually, when you put permafrost in seawater, your emissions in CO2 are much higher than what you do if you put it in the air. So this is a very breakthrough result in showing that you have a huge potential for this PCF now of chunks of frozen carbon that are now landing into the sea have the potential to be released as CO2. I'm saying have the potential because this is a lab experiment taken from samples from one location. This was the first attempt to do that. So we published a second paper now where we see something similar, but we don't necessarily see like that's something that spectacular. It might be in the range of the rates that you see for the terrestrial environment. But still, that shows there is a potential here for potential other feedbacks that we didn't really account for in the computation, in the projections that both Gustav and Sarah showed. So that's to open the door for further investigations. I think now what we want is to measure in situ what's happening, but measuring in situ gas emissions from the water surface in the Arctic when you have like only a couple of days a year to do that, and not to destroy the device that you paid very expensively with taxpayer money is a challenge, which is why we have to do that very carefully. And I conclude with this slide, and I'll now pass on to Marcus Carfen to conclude, I think, on this session today. Thank you.
While I wait for the slides, it's pretty stunning to see what can happen we back up some here. What can happen if we overshoot? I mean, in all the climate news that we're getting, we understand there are lots of hazards out there, but even to have yet another forcer out there that can carry us sort of over the edge where it's really hard to come back. I thought I would start this. Now I've changed the presentation pretty dramatically from what we had originally talked about, but I think it fits this better with a picture that captures one. I just really like the picture. And after this discussion, it's a little bit soothing to have something that feels a little bit more calm, but also includes sort of an image of a social ecological system, an Arctic ecosystem that includes people or traces of people, and people living in some kind of harmony with the space that they occupy. What I thought I would do is simplify through some simple visuals, and I really wanted there to be just a whiteboard that I could do these shapes on so that I could play with the shapes a little bit, but I was stuck with what was readily available within PowerPoint. But I want to talk about the social response to the human impacts on ecosystems that are coming back around to us, that we have ecosystem changes that we need to respond to. And how do we conceptualize those? And how do we act on the basis of that new information coming in? So let me explain to you a little bit about what each of these shapes is intended to capture. And hopefully those will stick with you when you leave, to think a little bit about how do we organize a social response to the kind of information, that the kind of knowledge that's been conveyed all day today, but this extra bump of what happens when permafrost thaws and accelerates the greenhouse gas process in ways that make overshoot really dangerous. So the first one goes back to what I talked about earlier, but it's the social ecological systems model that captures both people and ecosystems. And it doesn't go into detail about our dependence on the ecosystems, but it does take into account our influence on the ecosystems that we're utterly dependent on. So that's one piece. And I'll go into a little more depth in each one of these. The second one here, what I was trying to capture is a fork in the road, that we see the signals that come from these initial changes, but we interpret them very differently depending on our knowledge, also our interest, our space in the world. And those interpretations steer us in one direction in the fork or in another direction. We need to think about not only how we respond to this, but about how other interests in society are likely to respond. And we hear one of those already with the idea that we can pull ourselves back from being over the precipice by using technology, which is not a story that's very compelling after hearing the last hour's discussion. The third one is the straight line, and it's not really a straight line, but it's a progression over time when we think about policy, about knowledge being converted into policy, being converted into action. And my research has covered a whole range of changes in knowledge, policy, action over time that range from chemicals regulation, the European Union ban on asbestos, gender equality, food safety, voting rights, a whole range of different issues that follow a similar pattern over time. And it's useful to know what those tendencies are, even if they each have their own feedback loops, when we think about how do we persuade people based on this kind of knowledge. And the last one is, and this is not a very good representation, but the last one is nonlinear change. And we know that some of the changes have cliffs or tipping points that are very unfavorable, but there are also social change includes nonlinear change as well, that we need to be able to tap into. So a lot of the changes that are being set in place, you can think of electrification of automobiles, others that are now starting to catch wind power, a whole range of things that are starting to take off, and there are reasons for that. And we need to be conscious of that if we want to tap into the non-linearities that are beneficial and are essential if we're going to come out of this without a lot of, we won't call it just disruption, with a lot of pain and struggle. So let me walk through these a little bit, and I'll try to do it quickly because it's been a long day. But in each case, what I want you to keep in mind are these really simple images to be able to go back to and think, okay, what does that image represent in terms of human responses to these big ecosystem changes that we're driving? And this is just a listing of the things that I've just described. Iterative multi-scale social ecological processes, threat and opportunity, and our interpretation being dependent on our needs and our sort of positioning. The evolution of knowledge to policy to action. These things take time to sort of take effect and take off. And that the kind of processes that we need to facilitate, they're also not linear, but there are thresholds that we need to watch out for. This is this kind of social ecological systems model. And I don't want to pick on the natural scientist here too much, but what you see here is a model that we've actually heard a lot of this discussion over the past hour, where we're in the mix, but we're kind of, what we're doing is largely invisible. And to enable ourselves to really engage with that, we need to sharpen our picture of what's happening on the other portion of that cycle, that iterative cycle that continues on and on. So each of these sides of the cycle has its own life and its own processes and its own kinds of interactions. One of those sides has the advantage of operating by much more predictable rules. The other side operates by rules that are more changeable, much less predictable, but we need to understand the basics of them in order to be able to steer it more. So think very basically in terms of including us and our actions and reactions in that cycle, and reading more accurately what are the factors that drive those interactions. Those are really important. And any question that we take up, we'll see the nuances looking a little bit different, and in many ways similar to the nuances of the presentations that you've just seen. This is part of the reason why we need to bring in a mix of expertise into our projects, because none of us have the capacity to really take in all of the nuances in these processes in sufficiently well to be able to play out the scenarios that include people in some kind of variable scenario. So that's one. The second is this question of opportunity or threat. And my favorite example used to be, as the ice recedes, is that read as an opportunity to go in and do more development, or more drilling for oil, or digging of coal and exploration for fossil fuels, or is it taken as a warning? And the more interesting perspective here is, if you're sitting in a small boat, do you see this as a threat, or is it an opportunity to feed your community? Because you are waiting for this moment to be able to hunt this. I've been a vegetarian for 40 years, but paddling in water and seeing this made me really appreciate how hungry people must be to see this as an opportunity. But that, in fact, was the case, or has been the case, in some communities where you're waiting for this moment to be able to take the risks that come with being able to feed your community. But the main point is that these signals can be read really, really differently, and we need to understand better how those signals get read. This is a pretty mundane diagram, I'd have to say, but what needs to be understood is the first stage in this process is always defining the nature of a problem and establishing it as a problem that requires a public response. And that's what this last hour has really been. It's establishing a problem that people aren't paying attention to, and it's bringing in some metrics that give us a sense of it. But we really need to go much beyond this. We need to make this understandable in terms of people that are tangible to people who really don't get permafrost, and that reach into their lived experience in some way. So there are other kind of threshold phenomena that are similar, but I would argue coastal erosion is actually a pretty good one for many communities, but it doesn't reach everywhere. So these are things we need to think about. How do we connect this with people's range of lived experience, where the metaphor matches, where we can say, and this is what happens in the Arctic if we overshoot, because you can't take it back. But then there's another section of that phase that requires some sort of measures, and very often they're voluntary to start with. We've seen that in climate change. The first steps are always to say, please restrain yourself. I can use domestic violence as an example of this, that violence against women was initially a private matter that wasn't something subject to public policy. And it began to change when people said, well, if you did this to your neighbor, you'd be put in jail. And that started to catch, people started to think, oh yeah, this is really far from permafrost, right? But it made it tangible in a way that people could connect with and think, well, we should do something, and we should set up shelters, and we should take action to make to begin to ameliorate the problem. But it clearly wasn't enough, and extra steps needed to be taken to develop some kind of metrics that were not just to describe the problem, but help us understand, were we having an impact on the problem? And this fits a whole range of public policy issues. But we need to have some kind of a feedback mechanism to see whether what we're doing is getting any traction. Is it really having the kind of impact that we would like to have, or is it having no impact, or is it in some cases actually working in reverse? And begin to build that into the models. And then we come into a process where we see active measures that say, you can't do this, or we will incentivize doing good things. And it takes time for those things to be implemented, because they're never really good the first time around. I mean, think of most major policy initiatives that, the first couple of passes, they're an improvement, kind of, but they're often not very effective. So we have to layer on new things. And the real struggle with this is this stuff takes a lot of years. So we also need to think about how we accelerate it in the context of other steps being taken in climate change, so that we can move along. My main message here is this is not a straight line. It's also, there are feedback loops with each of these phases, but we need to think about it as a process where we intervene in the different stages to speed that process along. Not as kind of, we make new rules and yes, we can go home. And the other part is nonlinearity and tipping points. And I like to use Greenland examples because I have a bunch of really nice photographs of these. This gentleman was chief judge for the Greenland kayaking championships for many years. And he had a lot of interesting insights. But one of those, if you're paddling a kayak and you're having issues with stability, there's a threshold, not only for when you find yourself hanging upside down, but also for coming back again, where you get up to, there's a point right about here where whether you're coming up or whether you're going back down again. And we need to be able to be better at recognizing those thresholds. I see there are at least a couple people in the group who've experienced rolling a kayak. My specialty is the 270-degree roll. I'm really good at coming all around to here. And then the part that I'm working on is making sure the rest of it comes. But Campe was a real expert in watching how well people made that roll all the way back up again. But there's also an interesting social process, because they started this kayaking championship I wish I knew the exact date, but 20 years ago, as just a way to maintain some of the Greenlandic culture that has enabled people to hold on to part of what made Greenlandic culture what it is. And it started off as kind of a local club activity, but it's grown to an activity that's more global in reach. It draws people from all the countries that have a significant culture around kayaking, and it's become sort of an event. And I'm not sure whether it's really hit this threshold that it takes off, this kind of social process that takes off in the way that you would want it to, but it's built from very small seeds to something much bigger and much more recognized. And I think what we can say here is that we see other similar kinds of examples with electrification, with wind power. We need to figure out what the examples are around tackling permafrost. But one thing is pretty clear from what I've heard in the last hour, that we need to make sure people engaged in policy understand that capturing and storing carbon, even when that becomes sort of ready for prime time, is a real dangerous way of thinking about how we get ourselves out of this problem. It might be a good backup system, but we should not be planning on it to pull us back from way over the edge. I don't know how many people have seen this Roadrunner cartoon that I grew up with. Can I see some hands? You know, where the Roadrunner goes out way past the cliff. It's nice that some of you have seen it because it was really a favorite. And the wolf, or the coyote, follows the Roadrunner out over the cliff. The Roadrunner is fast enough to reverse direction and come back, but the coyote always becomes this little, and we don't want to be the wrong character in that cartoon. I'm going to close that by saying thanks, and thanks for the sort of knowledge and inspiration about where we need to go and where we shouldn't, and for all of you who've joined us for the not only the last few sessions but for the day. So thanks very much.
Whoops. Well, thank you very much to all the speakers. I would just like to know if there's any questions for any of the speakers from the hubs or also from the floor. So I have a question, and so it's a bit sort of left of field because my background's in parameterization of climate models, but I actually have a question on the modeling. So I was wondering if the modeler would be able to answer it. So if you come on the stage. So I'm just really interested from my own view, from my own research, how you model the spatial variability of the permafrost, especially because I'm aware that some climate models are fairly coarse resolution compared with the observations, the permafrost observations, obviously quite high resolution in comparison, and how you account for that. I was wondering if you'd be able to comment on that.
Sure. Yeah, I'll take this. Can you hear me? Yeah, I'll take this off though so it doesn't give her feedback. Yeah, so I would say that the models that are in like the CMIP6, so like the main ones that are in the IPCC report, they do not quantify the spatial variability of permafrost, except to maybe say that some fraction of the grid cell is wetland. But what my group and other groups are working on at the moment is a tiling approach. So a lot of these, if you remember the picture of the permafrost landscape, it's kind of almost like repeating units. So we can just, like, the idea is that we can just model that as like one of those units, and then that sort of scales up to represent the whole grid cell, if that makes sense. So it's like a couple of tiles representing, something represents like the hollow, something represents the raised part, and the interactions between them as well.
As sorry, so it has so on that individual tile, it has the correct statistical properties that you can then upscale to the whole grid cell. Yeah. Cool. Are there any other questions on the floor? Okay, in that case, I'd like to thank all of the speakers again. And unfortunately, we don't have a climate Kaylee for you tonight, but we are going to start again at 10 a.m. tomorrow, and I would love to see all of you there. Thank you.